Hello, my name is Leo. Today we are going to talk about electric current, voltage and resistance. Electric current, marked with big I, is directed flow of electric charge. Magnitude of electric current depends on amount of charge delta Q, which passes through cross-section of conductor within time interval delta T. Electric current is therefore proportion of delta Q and delta T. Its measuring unit is ampere, big A. From the formula that I is delta Q over delta T, we can get that Q is I times delta T, it as Q is IT, where we can get the measuring unit of electric charge equivalent to Coulomb, which is ampere second. And this unit is frequently, since ampere and second are standard measuring units of SI systems, while Coulomb is not. Electric current is a type of electricity called current electricity, where charges flow in one or more directions. There are two basic types of electric current based on their direction: direct current DC and alternating current AC. The main difference is that direct current flows only in one constant direction, while alternating current reverses its direction in regular periods with the form of sine wave. In this video we are going to talk about direct current. Electric current is actually a flow of electrons going from negative to positive pole of a source, but convention is the opposite and says the positive charges are those which go from positive to negative pole. We are going to use the conventional direction. We mentioned source. Source is one of the basic elements of electric circuit. Electric circuit is a circuit of elements, electrical components. The basic electric circuit has source of the constant voltage. On the picture on the right hand side is battery, a source with plus and minus pole. Load, such as resistor or LED lamp. Here is resistor marked with rectangle. And wires which conduct electric current marked as lines connecting other elements. It could also have a switch, an element used for switching flow of electrons, which is not necessary, so it is not in the circuit on the picture. The first Kirchhoff's law, also called Kirchhoff's current law, describes principle of conservation of electric charge in an electric circuit. It says that the sum of currents flowing into a node is in every point in electric circuit where current goes into three or more conductors is equal to sum of currents flowing out of the node. On the picture, currents I2 and I3 are currents flowing into the node, and their sum is equal to sum of currents I1 and I4 going out of the node. So from the equation of conserving of electric charges Q, we have that Q2 plus Q3 is Q1 plus Q4. We've got equation for conservation of electric current. So the same thing, but for I2 plus I3 is I1 plus I4, when the first one is divided by time interval delta T. We can also say algebraic sum of currents in a node is equal to 0, and it's marked using sigma notation, where is indicated that there is number of currents whose sum is 0. Just to say something about electric current on a microscopic level. We know electric current is a flow of charges passing through a conductor, commonly through some metal such as copper, excellent electrical conductor. Electrons have electric charge of approximately E, which is 1.6 times 10 to the minus 19th power coulombs, which is influenced by electric force F and is situated in electric field E. If we say S is area of cross-section of wire conductor, V is electron's velocity, E is electron's charge, and N is proportion of number of electrons located at unit of wire's volume, then we can get this formula. Voltage, marked with big U or V, is difference of potentials, meaning that U is phi2 minus phi1, where phi stands for electric potential. It is also change in electric potential energy per unit of electric charge, so U is delta EP over Q. Its measuring unit is volt, big V. There are two basic types of voltage, direct and alternating, which are, as we can see, the same two types as for direct and alternating current. In this video we are going to talk about direct voltage. However, two types of voltage within an electric circuit are voltage or potential drop and electromotive force. Voltage drop is a voltage reduction which happens when electric current goes through a passive element which only spends voltage but is not its source of an electrical circuit, such as resistors we are going to talk more about. In this way, energy from voltage source is distributed all over elements of electrical circuit. EMF or epsilon, electromotive force, is the name for voltage of source of electric circuit. This voltage is voltage of the circuit which is needed to keep the potential difference constant and to return charge on higher potential, which is done by converting chemical energy of the source, for example of the battery, into electric energy. It's actually a work per unit of electric charge as any other voltage. The second Kirchhoff's law, also called Kirchhoff's voltage law, does actually apply and is implied by the principle of energy conservation for closed path of current, that is electric circuit. It says the algebraic sum of electromotive forces is equal to sum of voltage drops caused by material resistance. It can be written in sigma notation as sum of all n voltages, which are both voltage drops and electromotive forces, is equal to 0. On the right picture, you can see 3 voltage drops and 1 electromotive force, so their sum is equal to 0. And here you have this expression for this. In all of this, you can ask yourself, how can voltage be negative? Well, before the calculation, positive direction of current, i.e. voltage, has to be determined. Let's say it's conventional current direction from positive to negative pole. Then imagine yourself going around the conductor wires of electric circuit. Since you've begun at positive pole, then when we come to the next source, if there is one, we have to come firstly to its negative pole in order for it to be positive. For this you need to know that when two batteries have opposite poles connected, then it's said they're connected in series, meaning the total voltage in the electric circuit is their sum. If two batteries are connected plus to plus and minus to minus pole, then you have batteries in parallel. Resistance. Electrical resistance, marked with big R, is a measure of resistance which a conductor offers to electric charge flow to passing of electric current. Its measuring unit is ohm with big letter omega, and its proportion of voltage and electric current we can see in the formula R is U over I. The inverse of resistance is conductance, which is ease rather than difficulty electric current passes through. It's marked with big G and is measured in Siemens, big S. Since it equals reciprocal value of resistance, formula for G is I over U. However, resistance is more commonly used physical quantity. Resistance not only depends on electric current and voltage, but also on temperature. This relation is expressed in formula that R is R0 times R0 plus R0 times alpha times T, where R0 is resistance at 0 degrees of Celsius, alpha is characteristics which depends on matter resistor consists of, and T is temperature. Alpha is always positive for all clear metals, meaning the higher temperature, the bigger resistance is. Exceptions are very low temperatures, when metal resistance almost disappears, as well as magnetic flux, we are going to talk more about, expulses, more precisely when metal is cooled down to temperatures below its characteristic critical temperature, which is phenomenon called superconductivity. There is also a quantity called resistivity, marked with a letter ρ, which is also property of a matter and is used in formula for expressing resistance using resistivity, length L, and cross-section area S of chosen part of conductor's volume. And here is the formula. What is Ohm's law? The formula R is U over I is another form of the formula I is U over R, which says electric current through a conductor between points of certain potential is directly proportional to voltage between the 2 points, where R is constant of proportionality, since U is I times R. This R is called, as we've already mentioned, resistance, and this formula is expression called Ohm's law. We can see on the graph and from the formulas that for the constant resistance, the bigger current is, voltage is also bigger, and vice versa. They are directly proportional. This dependence is actually exponential but is approximated to its most suitable linear form. There are two extreme cases of this law. First case is when resistance is infinitely big. Then electric current is infinitely small, so it's approximated to be zero. In this case, voltage is maximal and has actually value of electromotive force. The other case is when a resistance is zero. Then electric current is the biggest possible and it's called short circuit current. At the same time, voltage is zero. If we include resistance of source, here marked with little r, and electromotive force, which is voltage given by source, then we get Ohm's law for the entire electric circuit, which is written here. From this we can get also a voltage formula that U is this epsilon, electromotive force, minus I times little r. How we can get a wanted resistance in an electric circuit? The first way and the simplest way is to take a resistor of approximately wanted resistance. However, in most cases we'd have to combine resistors in certain way. There are two ways of how resistors can be connected, in series and in parallel. There are often circuits where series are connected with each other in parallels, or vice versa, so I'm talking about more complex circuits where both types of connections can be used. So the first type of connecting resistors is in series. In this one, resistors are connected to each other, so we can say in a row. In this case, current is the same in all parts of the circuit. So I is equal to I1, is I2, is I3, but voltage is divided over resistors in voltage drops. The bigger resistance of a resistor is, the bigger will be voltage drop on it. From this, we can set equations using examples of the circuit of 3 resistors connected in series presented on the scheme above. First, sum of all voltage drops, U1, U2 and U3, equals the total voltage U, which is actually source's electromotive force. And it is gotten by using law of energy conservation, this expression. Furthermore, using formula U is I times R, which is derived from Ohm's law, we can write that I times R is I times R1 plus I R2 plus I R3, and if we divide the equation by current IV, current I, which is equal at all resistors, we can get that R is equal to R1 plus R2 plus R3, which is formula for calculating total resistance in a circuit if resistance of the 3 resistors are known. The second type of connecting resistors is in parallel. Here resistors connected in this way presented on the scheme below. Here is voltage drop same on all resistors, so U is U1, is U2, is U3, but the total current is sum of all currents going through the resistors, because current I goes in 3 directions through 3 wires, so it's divided into 3 smaller currents, I1, I2 and I3, at the place of the 1 point, so at the node, and then is divided into 3 parts which come together at the second node, the right node on the scheme. Since we know that current is sum of these 3 currents, I1, I2 and I3, we can write these currents in a form using Ohm's law as U over R is U over R1 plus U over R2 plus U over R3, and if we divide this by voltage U, then we get the formula for calculating total resistance in parallel circuit. So we can see here that formula. I over R is I over R1 plus I over R2 plus I over R3. From this, calculate R as a reciprocal value of reciprocal values of the resistances of these three resistors. Work of electric current is an amount of electric energy converted into other forms of energy, such as heat when current goes through conductors. From the formulas for current, that current is Q over T, and voltage is W over Q, and Ohm's law, which says that U is I times R, we can get these formulas for work, W, of electric current. The formula that W is I squared RT equal to Q, where Q is in this case heat rather than electric charge, is called Joule's first law. This is the law which describes the process of releasing heat energy as a result of resistance which partly blocks flow of current. This getting of heat from electric energy is called Joule-ohmic or resistive heating. We have work of current, so we can also get its power. Power P is work per time interval, so W over T, and if we here put expressions for W, then we can get these formulas for P, power of electric current. There is theorem called maximum power transfer theorem, which says the power on a load in a circuit will be the biggest possible if the outer resistance, big R, is equal to inner resistance of source, small r. There are commonly used measuring units for expressing work except Joule, J, as the most conventional one. These are kilowatt hour, kWh, and electron volt, EV. First is kilowatt hour, which has actually this watt word in itself, which is measuring unit for power rather than for work. So 1 watt is 1 joule per second, and therefore 1 kilowatt hour is 1000, meaning kilo, times 1 joule per second, times 3600 seconds, which is number of seconds in 1 hour, which is 3.6 megajoules. This unit is used to express use of energy at constant power over time. It's used, for example, in expressing monthly consumption of electric energy in a household. Second is EV, electron volt, which is used by physicists who deal with particles of very small energy, such as electrons. Electrons do have the smallest energy possible, which is defined as 1 electron volt. We've already said that it is 1.6 times 10 to the minus 19 power joules approximately. Is defined as the difference in energy of an electron, which moves across potential difference of 1 volt. Finally, how we can measure electric current and voltage? We have measuring instruments for measuring both current and voltage. Galvanometer is an old device still used today, but in more advanced forms. It got its name after Luigi Galvani, a physician who constructed frog galvanoscope, so a device for detecting current consisting of nerve tissue from frogs' legs, which jerk whenever current goes through the nerves, it is whenever there is potential difference. However, today we don't use such galvanometers. Galvanometers are devices which can measure really low currents and voltages by conductor rotation in a magnetic field. Important properties of a galvanometer are maximal current, which can go through it, and maximum voltage. If any of these maximum values is exceeded, galvanometer can be damaged. On the right hand side you can see scheme of a galvanometer. Ammeter, also called milliammeter or microammeter, because it has range in order of magnitude of milli and microamperes, is a measuring instrument for electric current. Since ammeter can pass through itself very low currents, if we have source of high current, or at least current greater than maximal current load, then we have to come up with something which will take the biggest part of current so that it doesn't damage the ammeter. Therefore, if we have a high current source, then we have to connect a resistor in parallel with ammeter so as to divide current in two parts. The part of current which goes through ammeter should be maximally the value of maximum current, and the remainder part of the current should go through a resistor. For this resistor is crucial to have as small resistance as possible so that the biggest part of current goes through it. This resistor is in this connection called shunt resistor. Voltmeter is measuring instrument for voltage. If we want to measure a high voltage, meaning it's higher than the maximum voltage allowed for voltmeter, then we have to connect a resistor in series with the voltmeter. The resistor should have big resistance and has to be connected in front of the voltmeter in order to take the biggest part of voltage on itself, so that this first voltage drop is the biggest possible and the remaining voltage is smaller or equal to the maximum voltage allowed, and in this way voltmeter won't be damaged. There are concepts of ideal ammeter and voltmeter which are, as I've said, ideal, so they're only theoretical models of the instruments. An ideal ammeter should have zero resistance so as to measure the whole current going through. However, ammeters we use have a certain, even small, but there is a resistance, which is why ammeters always show smaller current than there actually is. An ideal voltmeter should have infinitely big resistance, so as not to pass current flow through. However, an actual voltmeter cannot have infinitely big resistance, so there is always current going through. In this video you've learned about direct electric current, voltage, resistance, work and power of electric current, and about how to measure or calculate these quantities. Thanks for watching and stay with us.